What's happening, folks? Geologist Philip Prince talking today about the Appalachian Mountains, specifically what is underneath them. Drew up this block diagram to give you a sense of how a geologist might think about what's under the Appalachians. It's showing a little bit more than 30,000 feet of rock down underneath the ground surface. This is showing you the area right around the North Carolina-Tennessee line around Johnson City. And this block diagram is just sort of a cutaway of the land surface as seen from Google Earth, and it is drawn to scale, meaning those layers and structures that are portrayed down under the ground are actually as big as they would be if you could cut the earth open like this. And this is a really interesting area to talk about because it has, among other things, so many rock types that have been brought together in so many interesting ways that ultimately builds up the volume of the upper part of the Earth's crust here. So in terms of finding a place to talk about how rocks from deep in the Earth that are granite-like, igneous or metamorphic rocks from many miles deep might end up sort of sitting up on top of sedimentary rocks like limestone and dolomite shale, this is the place to do it. Plenty other rocks represented here. The yellow has quartzite as well as some dolomite in it. Borderline metamorphic there, but generally speaking, layered stratified rock that should be sitting up on top of that gray granitoid stuff. But in many cases, as you can see, like right here, it's sitting down underneath it. And thinking about how these arrangements get put together is key to understanding this part of the world, is key to understanding a lot of Earth's mountain belts. And it's also going to give you a sense of what this crazy, interesting thing that is actually 20,000 feet under the surface, somewhere right on the North Carolina-Tennessee line actually is, and its significance. So in the course of this video, I'm going to try to develop how people figured this stuff out and why they would want to know what's so far under the ground here in Appalachia to begin with. Area you're looking at's right there, and if you look at the shape of eastern North America, you can sort of see the Appalachians sweeping along, going northeast, starting down here in Alabama, going all the way up into southern Pennsylvania in this view. And where we're looking is very much what we call southern Appalachia, really one of the iconic parts of the mountain range that's been studied quite a bit. And building up an understanding like this requires a lot of field work. It requires a lot of more technical investigation. But the fundamental takeaway when you see this is going to be age relationships are kind of messed up, right? The gray rock is the oldest. You should see yellow, orange, dark purple, and then light purple on top of that going up. And in a lot of places here, you've got these thrust faults that take an older layer, the dark purple in this case, and sit it on top of a younger layer, the light purple. There's quite a few of those, and it's ending up producing this sort of interesting like stack almost of geologic horizons that builds up the structure of the mountain range here. And you got to step back even further to really fully appreciate this. Now, I drew this diagram in paint, but it took a while. Can't reproduce something quite like this, I don't think, in the scale of the video, but area you're just looking at would be something like that. It's only part of this view, and this itself is only part of an overall assembled mountain range. More on that in a moment. But again, the takeaway here is a reversal of age relationships as you go down below the surface within the mountain range, right? So you get this kind of reversal of the geologic column where the oldest stuff, the gray, sits on top of the yellow and orange, which is younger. That sits on top of the purple, which is younger yet. And then the purple sits on top of the pink and green, which is even younger. So throughout the area that's portrayed here, older has been stacked up on top of younger, which has been stacked up on top of younger. And that is very much the theme of a mountain range like this. This is specifically a thin skin or thin-skinned mountain range. And what that term means is that the sedimentary layers, in this case, the orange, the purple, the pink, are very much involved in this stacking process. And in fact, the bulk of the mountain range is sort of sliding along in these sedimentary layers. And going to have to draw this out. So we're going to hop out into paint and try to diagram this up, give you a sense of where this sits within the overall scope of a mountain range, and also try to give a first look at this thin-skinned idea, which is really important to the overall understanding here. So hang on just a minute. All right, so here we are in paint. going to try to diagram out a couple of ideas here. First and foremost, just kind of the general appearance of a big collisional mountain range in the Earth system, and the fundamental details of that is you're going to have two big, thick continental plates sort of smashed into each other, and then the mountain range itself is going to be developed up above those, right? So the overall shape here is going to be kind of this wedge type of geometry, and all of the material that was in between these two plates is going to have been kind of pushed up and like stacked up on top of itself. So in this particular case, this is the big mountain topography here where it's kind of at its thickest. And then down here in the foothills of the mountains, you might see a couple smaller little ridges built up that are going to be comparatively pretty minor in terms of what they look like topographically, right? So that's the overall layout, and everything that we've been talking about so far is just going to be kind of over in one half of it, right? And to refine that even further, probably down into an area like this where you're catching almost kind of the core of the mountain range, but not quite, right? So when you see the block diagram and you see that first paint sketch, you're only looking at sort of like half, I guess, of the mountain range, and even sort of a smaller part of half, right? So we'll get that cleared out here. We may have to actually try to block that out completely, free up some space. That's going to do it right there. All right. So thinking in more detail about this thin-skinned idea, going to have to talk about the overall shape of the edge of the continent. See, something like this, continent's going to come along, and then it's going to have this kind of thinned down and broken edge right there, and we'll have big sequence of sedimentary layers sitting up on top of that. Throw in some layers here. Oh, like those. Get that sequence kind of thickening up as you move out towards the edge here. And you have sort of a different suite of sediment layers deep down there that are related to when this edge of the continent split apart from a supercontinent, right? This is what we call like a rifted margin or a passive margin. Good overall way to just kind of visualize what's going on here prior to Appalachian assembly. I've got to move my window there real quick. So what's going to happen here is that kind of the other half, or whatever you want to call it, is going to, we'll call that B, that's going to come along and crash into this edge of the continent there. We'll call that one A. And when this collision happens, it's going to break the edge of this continent like this and just push it all up into those sedimentary layers. And so we'll mark that in with a little more darkness there. Okay, so that's where continent A is going to break. And you can see as that black line goes flat right there in those sedimentary layers, that's going to be this thin-skinned idea, right? So we'll eliminate this because we're going to have to move collider B there and have it sitting up on top of this. Use that. It'll be, I like to use the thick white line there as kind of the eraser function. Okay, so now something like this. Remember that broken edge of the continent there? That's going to have been, pushed up something like this. You're going to see those two sort of chunks of the edge of the continent there. So part B is over here now. And this is sort of where things get interesting. So we'll have that bunch of thicker sediments there. They're going to be kind of wrinkled up here. They're going to be sitting next to B. It's possible that there's little remnants of B actually sitting right there. It's called a clippa. You see that in a lot of mountain ranges. We don't worry about that quite yet. And then out here in front, all those sedimentary layers have been just sort of shingled up on top of one another. A lot of ways to portray this. Sometimes you can have them being kind of like long and skinny where they'll slide for a long distance on top of one another. Sometimes it's like the first time where there's a lot of very small, closely spaced structures that bring them together. One way or another, like block this thing in. The sedimentary layers that have been kind of wrinkled up, they're going to make just kind of these little foothill ridges. And in some mountain ranges of the world, like the sub-Andes of Bolivia, this is a really big, wide area, very impressive to look at. And others like the Himalayas, particularly ones like the Himalayas where there's extremely rapid erosion, sometimes that's a little bit less developed. And then as you move back here towards the thicker part, the mountain range, you have this kind of bigger, more dramatic mountain topography built up, these big gorges. And overall, just kind of a grain that is less controlled by sort of that kind of shingled appearance of the sedimentary layers, right? So there's your basic thin-skinned structure, and the whole thin-skinned idea is all rooted around the fact that the sliding is happening in these sedimentary layers, and actually you have, we'll mark them in gray there, you have these chunks of continental margin that themselves have been pushed up and are sliding in those sedimentary layers. So the sedimentary cover on top of the continent, that's where it's all happening now. You can reproduce this very nicely in a physical model, like the one you're seeing here. Basic idea is the gray stuff is sliding up into those lighter colored layers, the kind of like white or yellow layers. And as this whole thing gets shortened, they're shingling and stacking up on top of themselves. That's exactly what's been sketched here. That's it happening in an actual physical sandbox model. All right, so back to it. Okay, so that's the general thin-skinned idea, where the sedimentary layering that sits on top of the continental crust is key to allowing this kind of stacking and repeating of geologic units, right? So it's possible to get younger layers pushed way down underneath much older layers, such that if you went down under the surface, you'd go down into older rock for a short period of time, but then you get into something much younger. And today's Appalachians are just a very eroded version of the initial drawing there. And when I say very eroded, like miles of rock is missing since sort of the peak of the Appalachians. The Appalachians are also topographically controlled, or topography, I guess, is controlled by geology. So metamorphic rocks, gray stuff over here, that makes the Blue Ridge. Sedimentary rocks, the purple and the pink and the green, make the Great Valley and Valley Ridge. The Appalachian Plateau out here is actually beyond the folding and stacking, and that is even younger sedimentary rock out there. So as you see this part of the world today, you're looking at geology, and fundamentally you're looking at the structure of the mountain range there. So if you took that sketch and turned it into its own block diagram and lay out something like this, few reference points in there, shout out to a few Appalachian cities, you can see that Blue Ridge topography matches up to certain rock types. The Great Valley topography with Interstate 81 running up it matches up with a big area of purple here. The valley and ridge is where you get the pink and green. There's a little more age range in the sedimentary rock there, so you get some more sandstone layers that make ridges. And by the time you get all the way out to Pine Mountain and the plateau here, you're basically in flat lying and even younger sedimentary layers. So this is the area we're focusing on because it offers this really cool transition from the really deep rock into the younger rock with the really complex stacking patterns that are so cool to think about here. So back to the block diagram, zooming in, what is this thing that's down 20,000 feet under the ground, right? Interestingly, the whole focus of interest there is just that little high point in the purple layer. The black lines here represent faults where the layers have broken and started to stack on top of one another, and just that little high point there in the purple is what people really cared about, particularly in the 1970s and the 1980s. It is about 20,000 feet under the ground surface. And the reason it's cool is it was thought to have the potential to hold natural gas. Geologic structures like this, these kind of convex up high points, call them anticlines. They are good at collecting oil and gas. In this case, because of the depth, even in the 70s and 80s, it was fairly sure if something was down here, it was going to be natural gas. And if you look at the overall structure here, well, there's plenty of options. The way that this is portrayed here, the green representing the natural gas accumulation is going to be sitting in limestone layers. It would be roughly middle Ordovician aged limestone, and there's plenty of options here based on this geologic interpretation, and they're deep and they're underneath rock that doesn't have anything to do with oil and gas at the surface, but you could go down and conceivably drill into and extract that natural gas. And you have to keep in mind, even though that little bump looks small, that purple layer is like 5,000 feet thick or something like that. The area you're looking at here is not the full block diagram. You're looking at like 15 or 20 miles or something like that. So the scale of rock volume that could be producing and feeding hydrocarbons into the top of those structures is really huge. And this was seen as like a worthwhile activity. So with all of these possibilities down underneath surface layers that most definitely would not offer any oil or gas potential, was a really cool idea because there's quite a lot of this and quite a long length of this geologic horizon that's stuffed down under these older rocks at the ground surface. So how do people like figure this out? The best answer there is really is based on seismic reflection. Have to use an energy source at the ground surface. It can be big vibrational energy. You can actually use like a controlled shot, a controlled explosion. Since seismic energy, seismic waves will travel down into the subsurface, bounce off of the different layers and materials down there and come back up, and you can collect that return with a receiver and process it up and end up with sort of like I don't know, like an X-ray or like a sonogram or something of what's under the Earth's surface. This one is, I think, from a little bit southwest of the area we're looking at. This is from a Bob Hatcher paper in 2004, certainly one of the most famous Appalachian geologists of all time. And if you look at that image, you can probably start to make out some of these patterns here that might remind you of those tilted layers we've been looking at. And if you zoom in a little bit closer, those ghostly images there are easy enough to see. Now, trying to build this up into the big picture understanding is a pretty significant undertaking, but it does require subsurface investigation like this to figure out what is literally miles underneath the ground surface, particularly when it's going to be a rock type that is very much unrelated to what's sitting up at the surface. And trying to understand what's down there has been kind of the big goal of Appalachian geology for decades. And what's been learned from it has sort of changed the understanding of mountain ranges around the world. Another paper from the 1980s. All this stuff it's work that was done in the 80s. It's old. People aren't really doing investigations like this very much anymore because it appears that the possibility of gas extraction from this setting is probably not gonna work out. But uh, this work here, Byron Kuhlander and Stuart Dean, 1986. One of them, I'm not sure if both of them were out of Wright State University in Ohio. it's an incredible publication where there's like 13 or 14 of these cross sections that go from from West Virginia, like well into Virginia, or from Tennessee, almost Kentucky, down into North Carolina. I mean, an absolutely mammoth undertaking to put all this stuff together. And you see a lot of those nice convex up shapes here in the cross section. This is up in Virginia, kind of Buena Vista area. And the idea here is also that not only might you look at these places out there in sort of the Great Valley or the Valley and Ridge, but you could be back here in the Blue Ridge of Virginia, like around the Blue Ridge Parkway or something like that. The rock at the surface is that old kind of granite like way down deep in the earth that has been pushed up and over the younger layers. You could drill down through that and get into this nice anticlinal structure at depth, right? So that was kind of the idea here. Again, that never worked out. To my knowledge, no one ever tried it. But at the time, the possibility of it was enticing enough that quite a bit of time and energy were put into to try to understand what's down there, right? So the interesting outcome of this is not so much that there was not gas down there that people are going to develop economically. Really, the cool outcome is that there is a huge amount of sedimentary layering that has been pushed way down underneath the Appalachian Blue Ridge and even the Piedmont. So this pattern here would go for many tens or even 100 miles or more out off the screen. So there's massive amounts of probably this limestone and dolomite, the purple layer there, that sit down under rocks that don't look anything like that, and rocks actually that should be underneath the limestone and dolomite, but have been pushed up and over top of it. Now, what's cool about this, talked about how thick that layer is. You're looking at about 25, 27 miles width here. This pattern extends much further. It extends hundreds of miles along the length of the Appalachians. And that purple layer, limestone and dolomite, that's chemically what it's made of. Calcium carbonate, CaCO3 is a limestone. The dolomite is CaMgCO3 within that CO3, there's a CO2 in there. And in fact, it's from atmospheric CO2 that these little micro ocean critters pulled out of the atmosphere, and they're in the ocean, turned into their skeletons and died and settled down and turned into these carbonate rocks, right? So takeaway message is that there's massive amounts of carbon dioxide that are stored in rock form within and underneath the Appalachians. And this is possibly something that goes on in other mountain ranges around the world. Likewise, there's a lot of carbonate rock that has been pushed up to the surface and has begun to weather and erode, so it's interacting with the atmosphere again. And taking this information and feeding it into climate models is a key point of understanding how Earth's climate and CO2 budgeting actually works to begin with. So even though the gas side of this did not work out, I don't think that's totally been disproven now. It's not to say somebody won't try that again, because the appropriate structures and the appropriate rocks are down there. But certainly it never did take shape, but the understanding that came out of it has been absolutely critical to taking climate change research kind of to the next level. And there's quite a bit published at very high levels out of universities that are taking the same kind of understanding and using it to make even better climate models. So it's like the information was very much not a waste of time. There's always something to get when you learn more about a place. Another interesting detail is that some of these geologic structures that might be good for oil or gas can also store carbon dioxide. It can be injected down into the subsurface. It's kind of like taking the gas out, but in reverse. This is a field of research that is picking up a lot of speed, and the idea would be that you'd capture CO2 from like a factory or something like that and inject it at high pressure, and it would be stuck down there many thousands of feet deep. In this case, sitting in that limestone, it's sealed in underneath that shale, and this stuff would be out of the atmosphere and not, making a problem anymore. And also, understanding how that might work requires this kind of oil and gas background. So it's a really cool way of thinking about what is under the ground, how mountains are put together, and how it all comes into play. And jumping out of paint one more time, gonna draft up just kind of like this basic mountain range structure. Going to do this one with a little bit more detail and talk about some of the structural changes that you see in similar mountain ranges around the world. Ultimately, elements of what you see here are going to be present in many of the Earth's big collisional mountain ranges. And that idea of thinking about what's down under the ground, particularly when it's in really big volumes and how that might impact the atmosphere as well as resources, is one of the main applications of geologic research. So we'll head back to paint. Hang on just a minute. All right, paint, back again. I'm going to try to put it all together. This is going to be tough. Wish me luck here, but I think we can pull it off. So we're going to start off with the same general idea. We'll have our block of continental crust here. I'm going to give that nice gray filling, and then we're going to have our other piece of continental crust that has been sort of pushed up and onto the first one. Okay, switch to the brush now and go ahead and kind of draft in what the surface of the ground would look like. Flat out here, then we'll start getting these outermost ridges, and time we get out here, this is where we're going to have some pretty high mountain topography, and we're going to turn this one into one of these kind of block diagram setups. Okay, so looking pretty good there starting off. Try to fill in a little bit of the geologic detail. I'm going to use a maroon layer here. So that's going to be the first of our sedimentary layers sitting on top of that gray continental crust. That color will contrast nicely there. We'll put an orange on top of that because it looks good. And this is also kind of a Virginia Tech shout out. Okay, so we've got our maroon and orange there. I don't like that. Do it again. All right, so we'll try to fill in a little bit of the white space there. Don't like that either. All right, that'll have to do for now. I got this zoomed in to 200% here, so the lines are relatively larger. So if you have the slightest shake in your hand, you got real problems. But that's gonna work for now, and we're actually gonna have orange kind of like thickened up underneath the edge of this thing, right? So now we'll fill in what's going to be sitting on top of the continental crust, and it's gonna be first and foremost the maroon horizon. And if you remember from the first black and white sketch, it tends to be thicker out here, and at this point, it's going to be a mess. It's had kind of a hard life. It's been sort of run over by the big piece that came in from the right side of the screen. So we'll have it thickened up there a little bit, and we'll keep that order going of having the orange on top of it there. Okay, no problem. I'm going to put a few form lines in this guy because it's kind of wrinkled and messed up like that. All right, cool. Very nice. So now, slowly but surely, going to have to start building in more of this sedimentary cover here. No problem. We'll do a dark blue next. I might try to keep that as a skinny line. Cool. And we're going to make that the layer where the sedimentary rocks have been thrust faulted on top of each other and repeated. Okay. Very nice. End up with something like that. And now we'll just have to start filling in above the blue. Now, question is, do you want blue on top of this structure? Yeah, you could have it there. It also could have been faulted away, sort of scraped away. We'll put it on this one. I guess if you surveyed mountain ranges like this around the world, sometimes in an area like this, you see quite a lot of the sedimentary section preserved in an area like that. We'll keep it there, whatever. Don't worry about it. All right, here come the pink. All right. Almost lunchtime here. Get me through it. This would have been much easier if I'd only made 2 or 3 of these things. Whatever. It's going to look good. Okay. Ooh, what's next? We'll do kind of a light green here. Okay. And the whole point of using all these different colors is to communicate that the sedimentary sequence is the same bunch of layers, just again shingled up, kind of stacked up on top of itself, right? I'm going to use this nondescript kind of straw yellow here. All right. Last one, fill in the spaces where the orange stuff is kind of like pushed up. Okay, nice. So overall structure is kind of coming together here. Go back to the polygon and let's fill in some landscape. I'm going to use brown for these higher up mountains. That doesn't necessarily mean that everywhere you go around the world, if you go in the higher mountains, there's just bare rock. A lot of places do have, a tree line or whatever with elevation, depending on the climate zone in the area, as well as how weather moves and things like that. You can end up with rain shadows and that sort of feature. Whatever. It's going to give good contrast here for what this is going to ultimately look like, and we'll fill in around edges there a little bit. Back to the polygon. My lower elevations here are going to be nice and lush and green. I don't like that. I'm clicking this here with like a kind of a stylus kind of thing. So you got to be sure your aim is good, and you got to be sure you don't click too close together like that, because it'll close your polygon before you're ready. But we getting it done one at a time. Ooh, very nice. Okay, we'll fill in some holes there. Cool. Okay, it's looking pretty good. So at this point, final touches, at least for the starting version here. We'll make this part of it kind of a different gray, but that's not necessary. That could also be sort of the same gray as you're looking at just underneath it there. Fill in a little bit of space here. And finally, we'll actually make this what we'd call a clippa. And what this implies is that had something like that, right? So that overlying kind of lid of gray has been arched up and the top's been off of it. So probably the most important fault structures in this whole thing are going to be those that I just drew in heavy black line there. And last touch, we'll throw some topography on it here. Down here in the foothills, these repeatedly tilted and shingled sedimentary layers, those are going to make low ridges, a kilometer or so of relief, probably not much over a kilometer of elevation, because settings like this tend to be fairly low in terms of their elevation. because the big thick mass of mountains toward the right there is actually kind of like weighing the Earth's crust down. Now, as you start getting closer to the higher mountains there, you're going to see elevation starting to increase, relief's going to start to increase, and there's going to be a little more topographic complexity to what's going on. And then finally, here in the real high mountains, there's going to be these kind of big, long, huge, monster deep river gorges, canyons, whatever, that are going to be coming sort of straight out of the mountains. And those are going to have massive relief on them, and the grain there is going to be different from what you see down in those parallel ridges in the tilted sedimentary layers. All right, final touch. A little bit of we'll do it with spray paint. We'll spray paint a little bit of snow up here. Yeah. All right, cool. So there's our highest mountains there. I don't know if I like that snow or not, but we're gonna keep it for now. Okay. Cool. Let's kind of blend that. Feather that out. It's a little bit too. Need the thicker spray can, kind of a more blurry effect. All right, back to the brush. Now we're set. Now we are set. All right. Cool. That's looking how we want it to look. Okay, so that's kind of the overall layout there of thin-skinned mountain range. And again, the kind of the thin-skinned idea comes down to what you see down there at the bottom. In this case, that orange layer is what all of the sliding is taking place in. And this part of such a range is really interesting. Broadly, that's the part we were looking at in the block diagram. In fact, that area would be something like that. This is a cool area because depending on what's going on underneath the gray, you can have all kinds of weird involvements of the sedimentary strata down underneath there. So one possibility would be, I don't know, we could just like make this huge thick pile. We'll say that orange layer has just thickened up massively by internal faulting down underneath here. So that's going to raise up like that. Okay, and that's going to push everything on top of it up higher to the point that you might end up not even seeing much of that maroon layer at all. It could almost push the gray all the way up the surface, right? So in this case, there's a lot more of that sedimentary rock volume down underneath the range there. Okay, so that's one possibility. We could do something more Appalachian-like. We'll fill this in just to give me a kind of a good blank slate there. So we'll bring that big fault back like that. And we could run, in this case, that pink layer all the way up there, the blue layer all the way under there, orange layer all the way down under there, and then the maroon layer all the way down underneath there as well, right? So there's another possibility. And that's something that's kind of like the Appalachians, because the pink layer there is pretty far up in the layer cake, but all of it is, everything over here is sliding in that pink layer. And today's Appalachians would be eroded, down to a level like maybe not that deep. Third time we'll get it, something like that, right? So what you're seeing today in Appalachia, of course, is quite different. So that's another possibility, and that puts a big long length of that pink, blue, orange, and maroon down underneath the mountains. Yet another possibility would be something that you see like in the Himalaya, and that's going to be just like an outrageous repetition of, in this case, we're going to make it, we'll make it the maroon and the orange. So we're going to build up just this gigantic stack of maroon and orange underneath here. Okay. And so this is going to be really big when it's all done. And there's going to be miles and miles of horizontal length incorporated into this big old stack here. So you're going to see something like that, and what you're going to do with the top end of it is tougher to know exactly how to terminate something like that. But one way or another, the idea would be that there's just massive, massive repetition of the same sequence of rock down underneath the surface there, and talk about piling up a lot of sedimentary rock in one place. This is sort of meta sedimentary because it's been deep enough, but you get the idea, right? So we'll try to bring these down so we can cut them off at the right angle, roughly. So something like that. All of that is sliding that way. And you could still then have one more maroon and orange sitting up on top of it there, because that will keep the age relationships where you need them to be. And then we'd have to kind of adapt how the gray is gonna sit over top of that, right? So there's yet another possibility of how you could do something like that. And important, lest I forget, the implication here is that that's going to be gray, and that's going to be sliding down in the maroon, and maybe briefly like climbing up into the orange there. There, oops. There we go. Come on. So yet another possibility there. So there's all kinds of interesting things that can go on underneath these mountain ranges that stack, repeat different layers. And what you're looking at here is again a massively, massively huge area. We'll draw the faults in that. So it's going to be maroon over orange. Okay, and then maroon over orange, maroon over orange, something like that. And you could keep that going actually until this thing like poked all the way out at the surface, and that is very much a Himalayan thing. So this is the basic idea. Hopefully this thing is cool to watch. I'm going to run it fast forward at the start of the video. It might be cool to watch it to build up there. But all of these are possible iterations, and this is how a geologist thinks about what's underneath the mountain range. As you heard in the video, there's a lot of reasons to consider that in an active mountain range, crustal structure. Once you get back in this area, it's like understanding possible earthquake slip locations, things like that. Looking further out, oil and gas, and all of it comes together, thinking about how these different earth materials get pushed down under and then lifted and eroded back out of mountain ranges.